Annyeonghaseyo 여러분. My name is Rupali Shinde. Today I am going to show you Hamming cone simulation using Jupyter Notebook. For installation, we have used Anaconda Python. Anaconda Python, from here I have used version 3.7. I can download here. After downloading Anaconda, go to Jupyter website, and from there you can see how to install Jupyter using Python and Anaconda. So this is the way we have used Jupyter Notebook. So now for our experiment we need one package. That package name is SCI DSP COM documentation. That means digital signal processing and communication. It is key used for DSP and communication. We can get release documentation about this package like this. You can learn many things. After reading all this documentation, we have moved to GitHub. From GitHub, we have cloned this package in our project. So cloning is done using Anaconda PowerShell prompt. As you can see, we have used git, clone and their address. So this is the way cloning into this package. After this finish cloning, we have started our next stage, and that is Jupyter Notebook. Simply type the Jupyter Notebook as I have shown here. It will go to your control to Jupyter. Jupyter runs on your server. It shows home page. Now this is my Jupyter home page. After coming here, take new Python 3. I want to use Python 3. Previously I didn't install package properly, so I have got error module not found FEK block. These are the packages and module in this package. So if we did not install it properly, we will get error like this. Now we have installed package correctly, and we move to next stage, that is implementation and importing package. So as we can see here, FEC block as a block, here it won't show any error because now our package is installed properly. Before we start with the Hamming code, let's start with the block code. Block code is a code with finite numbers. This means fixed length, means it is n. It is shown by n comma k. N is a information bit and k is a parity bit. Block code is shown by this diagram. So when this is block diagram of block code. So after coming down, there are single error correction in block code. There are two types of methods. One is cyclic code and one is Hamming code. For implementation, we need SCI DSP COM module called FEC block.py. As I have shown before, this was the error in my program. Each class has method for encoding, decoding and plotting. So cyclic code. Here n comma k cyclic code can be generated easily with n minus k shift register. This is the implementation of cyclic code. So here code rate is k by n. N is the length of the block code. So as we can see, length is going more, rate is going more. Means as length is increasing, rate is also increasing. And this is same applied for Hamming code. So Hamming we will not talk about more about cyclic code. Let's move on to the Hamming code. Hamming code is another form of single error correction. Hamming code uses parity bit to generate and decode block coder. Parity check matrix can be recorded to provide systematic code. So here it generates G. G is a matrix. H is a parity check matrix and G is generated matrix. G is always in K into N matrix, whereas H is a parity matrix. So after coming here, we can use encoder. So we can get in encoder we can get vector of length n code word. Decoder is slightly complicated. Decoder starts by parity check matrix H. Then it gives syndrome. Syndrome tells whether there is error or not. If it is 0, that means no error. If there is error in code word, the syndrome will tell us which bit have error. After the original source code can be decoded from the code word using following equations. So we are using FE block module and FE Hamming. Hamming code class description is used in block.fec Hamming. So we have run this using Jupyter. Here we can see we import packages, then we have 1 bit error into each code word and decode it. So this is the way we can run the code on the Jupyter. So let's check. We can copy this code, run on the Jupyter, paste it here. We have copy paste this code and it is showing output as Hamming code object. Now we want to generate parity matrix and generator matrix. So let's copy this code, paste it here and run using run button. So it will show you H parity matrix and G is a generator matrix. So move on to next stage. Here this is program for simulation and it is showing EBEP, bit error probability. This example generates random source bit, as we can show here. I have using random total. Then it will run till bit error is less than 100. This can be used to stimulate Hamming code with different rates. So we can see here condition. When condition satisfied, it stops. So in output we can see bit. So we will copy same code, paste it on your Jupyter, and run. As we can see, it's running the code. Bit error is 6, 19, 25. It's going up and up and up, and it stops when it's 102. Means it's bigger than 1. Its total bit error is and 100. When it is greater than 100, program stops. Let's move on to the representation. So here we are using FE block error probability bound. And we can compare it with the previous example. So here we are copy paste the code, paste it on the Jupyter, then run. As we can see, image, or we can say grid of 7 by 4 code, 15 by 11 code, and 13 by 26 code. So 7 by 4 is shown in this color, it's light blue. Purple color is 15 by 11, and 31 by 26 is from green color. So y axis is showing bit error probability, and as we can see, the code length is going higher, rate is going less. When 7 by 4 is length is more, and their dB is little bit more. So this is the way we can do Hamming code simulation using Jupyter. Thank you so much.